The next part of section 4.2 has to deal with the fundamental identities of trigonometric functions. So I've already been saying a lot of these as we've been going. I've been talking about the relationship between sine and cosecant, cosine and secant, tangent and cotangent. And I've also mentioned that the tangent is the sine over the cosine. So a lot of these I've been kind of working in as we go. The other identities that we need are in the basic reciprocal identities, right? We need to know that not only does sine equal 1 over the cosecant, but cosecant's 1 over the sine, right? So they're interchangeable. Basically, you can multiply and then divide to the other side, and you get those other relationships. And then the other ones that we didn't really talk about much were the Pythagorean identities. The most identifiable one, and probably the most important one for trig altogether, is sine squared plus cosine squared equals 1. And that directly comes from the unit circle. So remember that the unit circle's equation was x squared plus y squared equals 1. And remember that we said that x was equal to cosine of the angle, and y was equal to the sine of the angle. And so if we square those out, we get the Pythagorean identity. All right. The other two are related to that one, and I can show you how you get those as well. If you start with the original Pythagorean identity, and you just divide everything by one of the trig functions. So let's divide everything by sine squared. So just ignore the fact that they're squared for just a second, right? They're the same thing here, sine squared over sine squared, right? Or sine over sine, if you want to think of it that way. That's just 1. And cosine over sine, right? Because this can be rewritten as cosine theta over sine theta all squared if we use some power rules. And so what is cosine over sine? Well, if we look at the other identities here, cosine divided by sine is cotangent. So this is really cotangent squared. And 1 over sine, that's cosecant. So this must be cosecant squared. And if you look, that's the very last equation that's there. And you can get the second one, again, starting with the original Pythagorean identity and dividing everything by cosine squared this time. Sine over cosine now is the tangent. So this is tan squared. Then we have cosine over cosine. That's just 1. And 1 over the cosine is secant. So 1 over the cosine squared is secant squared. And that's the one in the middle there. So the nice thing is you can get the others if you just remember the first one. And then the other things you really have to remember are these 3 basic ones here. Sine is related to cosecant, cosine to secant, tangent to cotangent. And then you can just do the reciprocals of those and get the other relationships. So how can we use these? So here's an example. It says the angle T is an acute angle and sine of T and cosine T are given as the following. Use identities to find tangent, cosecant, secant, and cotangent. Where necessary, rationalize denominators. So this is very closely related to what we just did. So we have sine of T is equal to 24/25. We have cosine of T is equal to 7/25. So we know that the tangent, right, is sine over cosine. So that's 24/25 all over 7/25. Flip and multiply. These cancel. I get 24/7, and that does not reduce very nicely, right? So we just have to leave that. Then I would go ahead and do the cotan, because cotan is just 1 over the tangent. And so that's 1 over 24/7, or 7 over 24. Then we can use the other two, sine and cosine, for cosecant. Right, cosecant is 1 over the sine. So that's 25 over 24. And secant is 1 over the cosine, which is 25 over 7, right? We just get the reciprocals. None of these had any radicals, so there was no need to rationalize. So those are all 6 of the basic trig functions, and those are all calculated using sine and cosine. So let's take a look at yet another example. This time they give us an acute angle. It looks like there's a t missing here, so I'll just put it in, where the cosine of t is 3/7. Use a Pythagorean identity to find sine of t. All right. So cosine of t is 3/7. Well, the Pythagorean identity, the basic main one, was sine squared of an angle plus cosine squared of an angle must equal 1. So I can substitute this in for cosine and solve for the sine. So I have sine squared of t plus 3/7 squared equals 1. All right, so one thing that a lot of people struggle with, I think, is cosine squared t written this way is just the cosine of t then squared. Okay. So when I plug in, right, I'm just plugging in 3/7 and then squaring it. So sine squared of t is 1 minus, and let's do 3/7 squared is going to be 9 over 49. We need a common denominator over here, so we would do 49 minus 9 over 49. And that's 40 over 49. So I have sine squared t is currently 40 over 49. Remember, sine squared means that it's sine first, then squared. So I can take the square root of both sides, and I get the sine of t. Now, technically, right, I get plus and minus. And the square root here, let's see, square root of 49 and square root of 40. I'll split it up that way because square root of 49 is just 7. And then 40, let's see what perfect square can we get to go in there. I guess 4 is our best chance at simplifying that. So this is square root of 4 times 10, or square root of 4 times square root of 10, or 2 root 10 over 7. Looks like what we get for sine of t. And there's still a plus or minus here. Now, the problem did say that this is an acute angle if it's measured from standard position, which just means the positive x-axis. Right, so if it's measured from here, then we can take the positive. But if it's measured from anywhere else, it could be negative. So if it went this way instead, right, it could have been a negative. So we're just going to keep the plus and minus because it doesn't specifically ask or tell us where it's measured from. All right, so let's go ahead and continue on here. This asks us to evaluate the cosine of 22 times the secant of 22 degrees, without a calculator. So this might look like a daunting task, but there's one thing we can use, which is that secant is related to cosine, right? The secant of an angle is equal to 1 over the cosine of that angle. So I can just multiply, instead of by secant, I can multiply by 1 over the cosine. And because they're the same angle, right, I end up with just cosine of an angle, specifically 22 degrees, over itself, which is just 1. All right. Let's continue on to this one. So we have cosecant squared and cotangent squared. So off the top of my head, I don't know exactly what that is. Right, I'm cosecant and cotangent, they're not functions that we deal with very often. At least they're not ones we happen to know off the top of our head all the time. So how can I relate these to the trig functions that I do know very well, sine and cosine and tangent? Well, cosecant, right, is 1 over the sine. So this becomes, and because it's squared, it's just sine squared. So 1 over sine squared of pi over 11 minus, now cotan is 1 over the tangent, or in this case, I think we're going to want to use the relationship that it's cosine over sine. So that's going to be the cosine squared of pi over 11 divided by the sine squared of pi over 11. All right. Now, again, because these are common denominator, I can put them together. And you might be thinking, oh no, I have no idea what cosine or sine of pi over 11 is. But don't fret, right? The Pythagorean identity said sine squared of an angle plus cosine squared of an angle is 1. And I can rearrange this and it's still true. So I can subtract the cosine squared from both sides. And that means that sine squared of theta is 1 minus the cosine squared of theta, which is exactly what I have here. I have 1 minus cosine squared of pi over 11. That's equivalent to the sine squared of pi over 11. So again, just like the last example, I end up getting 1. All right, so the last part of section 4.2 is dealing with what we call even and odd functions, and specifically, we're talking about the trigonometric functions. So note on the unit circle that the value, right, if I look over here at the unit circle, I get t, right, angle t or arc t, if I go in the positive direction, and I get negative t if I go in the negative direction. But the x-coordinate to get to those points is exactly the same, and the y-coordinate is opposite, right? The y-coordinate would be plus on this one, minus on that one. So that right there tells you that the sine, since it gives the opposite, right? It's related to the y-coordinate. Sine is an odd function, and cosine, because it's related to x, gives you an even function. To prove this, we need to show that for an even function, the original function equals when I plug in a negative. And for an odd, that's when plugging in a negative is the same as taking the negative of the function. Now, I'm not going to ask you to prove those in this instance. We're just going to use the facts. So sine of a negative angle is negative sine of the angle, and cosine of a negative angle is that angle. Because cosine is related to secant, right? Because the cosine is even, secant's also even. Because sine's related to cosecant and sine's odd, cosecant is odd. And then because tangent is a combination of the two, an odd divided by an even, tangent's also odd. And because tangent is related to cotangent, cotangent's odd. So basically cosine and secant are the only even functions. All right, so they're going to say here, evaluate each expression using even and odd properties. Don't use a calculator. So first we need to use the even and odd, then we need to use the unit circle. So again, let me bring that back. All right, so we want sine of negative 120. Let me just make this a little smaller over here so we can see the entire unit circle. All right, there we go. So we want the sine of negative 120. Well, sine is an odd function. So odd means the negative on the inside can be taken out and put in front of the sine. So now I need to figure out what's the sine of 120 and take the negative of it. So sine of 120 degrees, that's the y-coordinate. That's negative root 3 over 2. I'm sorry, it's root 3 over 2. And then I'm taking the negative of it. So we get negative root 3 over 2. All right. That was not so bad. Secant of negative 3 pi. All right, secant is related to cosine. Cosine is an even function, so is secant. Even functions don't care about the negative, so this is the same as secant of 3 pi. Now, again, 3 pi is not on the unit circle. You could technically do 3 pi minus 2 pi and find the secant of pi, or we could just go, here's pi, here's 2 pi, there's 3 pi, which puts me back here. And the secant's related to cosine. All right, this is 1 over the cosine of 3 pi. And the cosine is x. So in this case, the x is negative 1. So we get negative 1. Here we go again. So we have cotan of negative 17 pi over 6. Cotangent's related to tangent. They are both odd functions. So the negative comes out in front. 17 pi over 6. And we did this one earlier. So we can do 17 pi over 6 minus 2 pi, which is 17 pi over 6 minus 12 pi over 6, or 5 pi over 6. So this expression right here is equivalent to negative 1 over the tangent of 17 pi over 6, or negative 1 over the tangent of 5 pi over 6. So then we just need to locate that in the unit circle. So 5 pi over 6 is right here. Tangent is y over x. So that's 1/2. I'm not sure what's. Here we go. 1/2 over negative root 3 over 2. So we got to do some manipulation there. So let me just come down here. We have some room. So this is negative 1 all over 1/2 times negative 2 over root 3. The 2's cancel. So now I have negative over negative. That's positive. And I have 1 over root 3, or root 3. And I think that concludes section 4.2.